So we're going to take a look at an example that asks, what is the temperature at which solid sodium chloride melts? And it says that the solid and liquid states are in equilibrium at this temperature. So I'm going to underline that because that might be pretty important. Okay, and it says the enthalpy is 30.3 kilojoules per mole and the entropy is 28.2 joules per mole Kelvin. So first, figure out what it's asking you for. So it's asking for temperature, which is T. And we are given enthalpy and entropy. So delta H is 30.3 kilojoules per mole and delta S is 28.2 joules per mole times Kelvin. Okay, so what we're going to do is we're going to try to figure out, what we're going to do to find temperature. So we know that it is at equilibrium. Okay, and we know that we're finding T, we have delta H, we have delta S. So looking back at the equation, delta G equals delta H minus T delta S. Right? This is the equation that we're going to use. Okay? And at equilibrium, delta G equals 0. Right, because it is at equilibrium. Okay, so now we know then that 0 must equal delta H minus T delta S, and we're solving for T. So now we could plug in our delta H and our delta S, but before you do that, always check units. Okay, always check your units to see if you need to convert anything. So if you take a look, we have kilojoules, we have joules. Okay, we want to put it in joules. It's just easier to work with your joules. So if we put this in joules, we have 30,300 joules per mole minus T times 28.2 joules per mole times Kelvin. Right, so what you can do is you can add this 28.2 times T, add this to the other side, solve for T, and what I found for T is 1070 Kelvin. And if you want to convert that to Celsius, you can, but you might as well just leave it in Kelvin. What this is telling us is this is the melting point of sodium chloride. So anything above this temperature, it's melting. Okay? Anything above this, melting is spontaneous. Anything below this temperature, melting is not spontaneous. Alright, so we know the melting point now of sodium chloride. From that, you could tell if something is spontaneous, because obviously if it's less than the melting point, it's not going to melt. So this is just a type of question that you could be given using this delta G equals delta H minus T delta S. What I would recommend doing is lay everything out like we did here. Okay, what are you trying to find and what are you given? Because that could give you a really good idea for the equation that you're going to need. So again, here is the answer written out a little more nicely, so you can take a look at everything, but it's what we had just discussed. Okay, so example 8 says at 298 Kelvin, delta G is negative 190.5 and delta H is negative 184.6. For the following reaction, calculate the standard entropy, which is delta S, for the reaction. So again, I'm going to lay everything out. We know 298 is T, we have delta G, we have delta H. Okay, so calculate the standard entropy. We're going to use delta G equals delta H minus T delta S. So I know delta G, I know delta H. Now notice these units are the same. That's fine, because when you subtract and when you divide, you just want to use the same unit that comes out, but as long as you have the same, as long as you have kilojoules for both, that's okay. So we have negative 190.5 kilojoules equals negative 184.6 minus T, 298, times delta S. So again, you rearrange, move variables from one side to the other. So move the 298 delta S over, add the 190.5 to the other side, divide, and you find that delta S is equal to 0.020 kilojoules per Kelvin. Alright, 0.020 kilojoules per Kelvin. But typically, entropy is given in joules per Kelvin, so we would just need to multiply that by 1,000 to get 20 joules per Kelvin. So again, another example of using your delta G equals delta H minus T delta S. Again, lay everything out that you have to figure out what equation you'll use. And so again, here are the answers typed up, so a little easier to read. But again, same thing we just did on the slide before. So what I'm going to do now is actually work an example for you. This is not in your notes, but I just want to go through an example for you just so you can see the thought process as you would go through calculating delta G. So it says to use the data from Appendix C to calculate the standard free energy change for the reaction. So this wants delta G naught of reaction. Okay, and we know based on this equation, okay, and based on Appendix C. So remember delta G naught of reaction is products minus reactants. And you need to take into account the coefficients. So delta G of reaction equals, okay, so 4 times the delta G of PCl3 minus the reactants. So we have P4 plus 6 times the delta G of Cl2. So now we want to look up these values in Appendix C. So 4 times the delta G of PCl3, so if you look in Appendix C under phosphorus, it shows us that delta G is negative 269.6, okay, minus P4, which is 24.4, plus delta G of Cl2. Well, chlorine, that's its standard state. Okay, so it's 0. So we have 4 times negative 269.6 minus 24.4, and we find that delta G naught of the reaction is equal to negative 1102.8. Okay, and then what we need to do is figure out what these units are. Your delta G in Appendix C is given in kilojoules per mole. Okay, so that is your unit. So the standard free energy change for this reaction is negative 1,102.8 kilojoules per mole. And again, it's important to notice that the delta G of Cl2 is 0 because that's its standard state, but P4 is not commonly given as P4. Most commonly, phosphorus is simply P4 solid. So because it's P4 gas, that's not its standard state. So it is important to remember that anything in its standard state is 0. So now with example 9, you are given the delta G value for the following phase changes, and I want you to tell me whether it's spontaneous. So what you have to look at when you're determining spontaneity and delta G is the sign. Okay, so again, delta G being less than 0 is spontaneous. Delta G greater than 0, not spontaneous. And if it's equal, it's at equilibrium. So if we take a look at A, at 283 Kelvin, the delta G is negative 250. Negative 250, it is spontaneous. Okay, and again, that's because it's negative. For B, at 273, it is 0. Well, that's at equilibrium, so there's no net reaction, right? No change because it's at equilibrium. And then C, if delta G is positive, it is non-spontaneous. So you can actually consider delta G to figure out if something is spontaneous based on the sign. Okay, so again, negative, it's spontaneous. Positive, it is not spontaneous. So in this final example, you are given 3 free energies of formation of glucose, CO2, and H2O. So I've given you the delta G for each of those, and I want you to calculate delta G for the oxidation of glucose, and I've already given you the equation. So what you need to do is figure out, I need to solve delta G, and I'm given this information, right? I'm given the formation's free energy. So what I'm probably going to use is delta G of reaction equals the sum of delta G of products minus sum of delta G of reactants. So what I'm going to do is I'm going to take a look at my products. I have CO2 and H2O. Right, so delta G is equal to 6 times the delta G of CO2, which is negative 394.6 kilojoules per mole. Okay, plus, because we have to find the sum, 6 times delta G of water, which is negative 237.2 kilojoules per mole. Okay, so there's my sum of products minus the sum of your reactants. So the delta G of glucose is negative 907.9 kilojoules per mole plus 6 times delta G of oxygen. but there's no oxygen up here. Why isn't there an oxygen here? Well, it's because it's in its most stable state, so it's 0. Okay, so you have the sum of your products minus the sum of your reactants. Take into account the coefficients, and you find that it is negative 2,882.9 kilojoules. Okay, so again, the reason it's just kilojoules here is because you multiply by the coefficients. So when you multiply by the coefficients, that gets rid of your per mole. And notice that in parentheses it says it's spontaneous. Well, think, how can you tell if something is spontaneous? It's if delta G is less than 0. So because delta G is less than 0, the oxidation of glucose occurs spontaneously. That's good for you, because that means when you take in sugar, your body oxidizes it and uses up that sugar to produce CO2 and H2O. That process is actually called glycolysis, which is the initial stage of glucose metabolism. So a little biology added into our delta G information for today. So this is the last example that we're going to go through together. What you guys will do tomorrow is you guys will practice more with calculating delta G. As you can see, it's very similar to calculating entropy, but we did not go through the third type of problem. So third type of problem is like Hess's law. So if you remember Hess's law, if you multiplied an equation by a factor of 2, say, then delta G is also multiplied by 2. If you flip a reaction, then delta G changes signs. And then if you can have a series of steps all create an overall reaction, right? That's what Hess's law does. Then you have to add up all of your delta G's. So you'll look at some of those tomorrow, but know that there is a third type. Please write down any questions if you have them, and then we'll just continue to do more practice.